Turbocharging has revolutionized the automotive industry by enhancing engine performance and efficiency. Smaller engines may now generate much more power and torque without growing larger or heavier thanks to turbochargers, which force more air into the combustion chamber. This technology is essential to contemporary performance cars since it not only increases performance, but also lowers emissions and improves fuel economy. In this video, we will go through 7 key points that highlight how turbocharging transforms performance car engines. Increased power output. By utilizing the energy present in exhaust gases, turbocharging radically alters the power dynamics of internal combustion engines. The engine's design and atmospheric pressure limit the amount of air that can enter the combustion chamber in a normal, naturally aspirated engine, which limits the engine's capacity to generate power effectively. In order to force more air into the intake manifold, turbochargers use a turbine powered by exhaust gases to rotate a compressor. A larger volume of air-fuel mixture can enter the combustion chamber as a result of this process, which also makes the intake air denser. As a result, without increasing engine displacement, this permits a more potent combustion reaction, leading to noticeably higher horsepower outputs. A 2.0-liter turbocharged engine, for instance, can produce up to 300 horsepower, whereas a normally aspirated engine of the same capacity might only produce 150 to 200 horsepower. Improved fuel efficiency. The capacity of turbocharging to maximize the energy produced from fuel makes it inherently connected to increased fuel efficiency. Larger displacements are frequently required in conventional, naturally aspirated engines in order to attain a higher power output, which usually leads to increased fuel consumption. This implies that, in comparison to larger engines, less gasoline is required to produce power outputs that are comparable to or even better. Many contemporary compact cars with turbocharged engines, for example, can achieve remarkable fuel economy ratings, often surpassing 35 miles per gallon on highways, while their larger, naturally aspirated counterparts might find it difficult to reach 25 to 28 miles per gallon in comparable circumstances. Reduced engine size and weight. One of the most revolutionary benefits of turbocharging in automobile engineering is its capacity to reduce engine designs without compromising performance. Larger engine displacements were historically needed to provide high power outputs, which increased vehicle weight and complexity. In addition to making cars lighter, this trend of downsizing also greatly enhances handling and road agility. For instance, a lot of high-performance sports cars now use turbocharged 4-cylinder engines rather than the more cumbersome 6 or 8-cylinder models. This change not only lowers the center of gravity, but also decreases weight, which improves overall vehicle dynamics and stability when cornering. Enhanced torque delivery. The capacity of turbocharged engines to produce significant torque at lower RPMs than naturally aspirated engines is one of their most remarkable characteristics. In conventional designs, drivers must crank the engine somewhat before they get the best acceleration, because peak torque frequently happens at higher RPMs. Due to the increased air density produced by forced induction, turbocharged engines alter this dynamic by producing maximum torque at significantly lower RPMs, frequently around 1,500 RPMs. When drivers accelerate from a stop or during passing maneuvers on highways, this feature translates into instant responsiveness. It enables quick acceleration without requiring a downshift or a significant increase in engine speed. Better emissions control. With increased environmental consciousness and more stringent car emissions rules, turbocharging has become a viable way for automakers to satisfy these requirements without sacrificing high-performance automobiles. The capacity of turbocharged engines to mix fuel and air more efficiently within the combustion chamber, a consequence of the increased air density brought about by forced induction, usually results in greater combustion efficiency. Fuel burns more thoroughly as a result, and dangerous pollutants like carbon monoxide, nitrogen oxides, and particulate matter are greatly reduced in emissions. Additionally, turbocharged engines can reduce overall vehicle emissions since they can produce greater power with smaller displacements than larger naturally aspirated engines, which may require more fuel for comparable performance levels. Nowadays, a lot of manufacturers combine turbocharging with cutting-edge pollution control technologies. Such selective catalytic reduction systems to improve environmental performance even further while preserving driving thrill. Turbocharged engines are positioned as a crucial technology in the automotive industry's shift to cleaner alternatives because of their combined emphasis on sustainability and performance. Versatile performance across conditions. Modern automobiles must function well in a variety of circumstances, and turbocharging offers remarkable performance versatility across a range of driving conditions. Because turbocharged engines can force more air into the combustion chamber, regardless of external conditions like altitude or temperature changes, they can maintain consistent performance unlike naturally aspirated engines, which may struggle at higher altitudes or under heavy loads due to decreased air density affecting power output. They are especially well suited for a variety of driving situations because of this capabilities, from interstate cruising where sustained high speeds are required without losing power during climbs or overtaking maneuvers to urban commuting, where rapid acceleration from stops is required. Advanced technology integration. The growth of turbocharging technology has been defined by substantial breakthroughs that boost both efficiency and performance qualities in current cars. In order to improve responsiveness in a variety of driving situations and reduce lag, a common problem in older designs, where there was a noticeable delay before boost was delivered after throttle input was applied, modern turbochargers frequently integrate advanced features like variable geometry turbines and electric assist systems. In contrast to traditional fixed geometry designs, which were unable to adapt quickly enough to abrupt changes in throttle position or driving demands from drivers seeking immediate acceleration response when needed most urgently during passing maneuvers or merging onto highways safely without hesitation due to delayed boost delivery times experienced previously with older technologies used prior to advancements introduced recently into today's automotive market landscape. Variable geometry turbines dynamically adjust their blade angles based on engine speed and load conditions, allowing for optimized airflow at both low and high RPMs. In summary, turbocharging is an essential technology in contemporary automotive engineering since it not only improves engine performance, but also increases efficiency and lessens environmental effect. Thanks for watching our video, and don't forget to subscribe.